Okay, so and then yeah, we are very pleased to have you both here to talk to us, and yeah, I would give the word to you, and afterwards I hope we have hopefully a good discussion.
Okay, thank you very much for the invitation to participate. It is an honor for us to be here virtually. My name is José Fernández, and the second presenter is Alfonso García.
Good afternoon, everybody.
As I mentioned, I am José Fernández. I am the creator of this methodology that is called ISE&PPOA. And this methodology is based on my experience as professional and professor in developing systems, mainly software-intensive systems for avionics, cellular phone applications, control and data acquisition for nuclear power plants and coal power plants, and humanitarian vehicles. Alfonso is an independent consultant. He has a master's degree in industrial engineering from University Politécnica de Madrid. He is in COSI certified systems engineer. Alfonso has more than 30 years of professional experience as systems engineer, architect, and consultant. He was involved in different engineering projects, including air traffic management, avionics, automotive, and elevation systems, using both classic systems engineering and model-based systems engineering. The agenda of this presentation. First, I will explain briefly, because we have no time, the foundations, the conceptual model, and the methodological process of this methodology that is named ISE&PPOA. I will devote some time to heuristics. Heuristics is a very important topic in this methodology. The topic is the best practice we use to implement non-functional requirements. But the main topic of this talk is functional architecture. So we will explain more in detail how we face the problem of developing the functional architecture. That is one of the main difficult artifacts to create. And Alfonso will illustrate it with an example of an electronic parking brake developed with the Cameo tool. As you know, a methodology is a collection of processes or steps to perform some activities, that these activities use some best practices or methods and use as well a tool. The tool is important, but it's not the most important thing. The most important thing is to teach engineers how to think. In our case, the methodology ISE&PPOA is tool independent. We have used diverse tools. Currently, we are using Cameo, but we are using another tools. For example, Rhapsody, Visual Paradigm, and Microsoft Visio. So for us, the tool is not the important matter. The important matter is to teach engineers how to think, how to solve a problem. This methodology I see the name is integrated systems engineering. Pipelines of processes in object-oriented architectures integrates. First, was developed by myself as an architectural framework for software-intensive systems that was called PPOA, and after it was extended to include model-based systems engineering. This is the reason of the name, this strange name, Integrated Systems Engineering and PPOA. This methodology is requirements-driven, so requirements are very important because you develop the requirements at the same time as the architecture. The two processes for creating the requirements and the architecture are intertwined. So the important thing, as I mentioned before, is to learn to think consistently. This is the reason of the use of methodologies. And the methodologies are not an obstacle for creativity. Creativity is guaranteed. There are some decisions that have to be made by the engineer. For example, Alfonso, we will explain that in the functional flows, the control flow is a decision of the engineer. It's based in diverse aspects. So a methodology is not an obstacle for creativity. It's very important to understand that. This methodology works in 3 dimensions: the dimension mission, the dimension of system, and the dimension of software. The dimension of system, in the mission dimension, we see the system from the outside. The system is for us a black box. It's a black box where some actors interact with the system. This interaction is described by scenarios. From these scenarios, we obtain user needs. From these user needs, we group them into capabilities. The other dimension, we see the system as a glass box. In this dimension, we obtain the system requirements, and we obtain the functional architecture, where we represent functional hierarchies, and we represent functional behavior by representing functional flows. We represent the physical architecture as well, using block definition diagrams for the physical hierarchies and internal block diagrams for representing the connections between the parts of the architecture. In software-intensive system or software-intensive subsystems, we use the software dimension. In the software dimension, we represent first the domain model. The domain model is the bridge between the system dimension and the software dimension. The domain model is a representation as a class diagram, UML class diagram, of the main classes that will be implemented as software components. These main classes are identified from the functional architecture, from the functions to be implemented by software. This is very interesting how we reach the system dimension with the software dimension. Some other methodologies don't give some help or some guidelines to do that. And in this case, it's very important, the domain model. I have not time to explain it, but in the web page, you have examples. And if you have questions, you can send to me an email. In the software, we represent also a structural view of the components of the software and a behavioral view. For the behavioral view, we use, in both cases, in the system dimension and in the software dimension, we use activity diagrams for representing behavior. It's important to understand that this methodology is requirements driven. What do we mean by that? We mean by that we represent at the same time, we are building the architecture, the system architecture, and building the requirements flow down. When we have the system requirements, we obtain the functions from the system requirements. We represent these functions with a functional hierarchy, and we allocate these functions to different subsystems at the subsystem level. With these subsystems and the non-functional requirements are useful for implementing these connectors between the subsystems. So the non-functional requirements are drivers of architectural decisions. When we have the subsystems, we specify the requirements at the level of subsystems. With these requirements, we go to the next level. We go to this level and we identify new functionalities of lower level. These lowest level functionalities are allocated to inside the subsystems, to subsystems blocks, subsystem blocks and parts in this case. So new functionalities are allocated to new blocks, and we represent the architecture of each subsystem. We use here internal block diagrams. With this information, we specify the requirements of each of these parts of blocks. With this requirement, we go to the next level, that is detailed design. In this detailed design, the specialty engineers, mechanical engineers, electrical engineers, or software engineers design each component based on the knowledge of this specialty. To understand a methodology, it's very important to have a conceptual model or ontology representing the main concepts related to the methodology. Here is the conceptual model, also explained in the methodology book in the chapter 4. In this conceptual model, we have a system, the system of interest. Our system of interest interacts with an environment. This interaction is described by association class, that is the operational context. In the operational context is an aggregate of scenarios of use cases. From these scenarios, we obtain needs. We obtain needs that are requirements, but from the point of view of the actors. The subject of these requirements are the actors, not the system. These needs are grouped into capabilities. Capabilities is a complex concept we use in the aerospace, mainly in space systems and defense systems. Capability is the ability to perform something. It's related with the mission. These capabilities group some properties. These properties may be quality attributes, maybe states of the system, maybe physical properties or functionalities. For example, I put this example from the aerospace. Is very, if we have the capability long endurance in a humanitarian vehicle, this capability is a set of properties. For example, long endurance is guaranteed by a physical property, that is the wingspan, a long wingspan from the aircraft, to have less resistance, to have less aerodynamic resistance. We need another quality attribute, that is, for long endurance, it's very important to have high reliability of the components of the humanitarian vehicle. And also, we need functions related with health monitoring. So, long endurance as a capability is a complex property that has different attributes as quality attributes, functionality, and physical properties. These attributes are represented by requirements, and these requirements are allocated to system parts. But in the case of non-functional requirements, you cannot allocate them because there are, in some cases, emergent properties. So non-functional requirements are implemented using heuristics. I will explain this later briefly. This is a matter I will explain more in the book, and I will explain in COSI International Symposium 2021 with an example of a medical device. So this is a summary of what I explained before, so I will not repeat. A methodology has a methodological process. In this case, is the methodological process from a high point of view, high-level point of view. In this methodological process, we first identify the artifacts related with the mission dimension, mainly operational scenarios and capabilities. With these artifacts or high-level requirements, we build in the system dimension what we call the functional architecture. And the functional architecture has three artifacts: hierarchies, N-square charts, and functional flows. When the functional architecture is complete, it means that all the outputs have one function that produces them. You go to the physical architecture. The first version of the physical architecture is the what we call the modular architecture. The modular architecture is when we allocate the functionalities identified here to modules with the principles of high cohesion and minimum coupling. When we have the functional architecture, we try to implement the non-functional requirements. For implementing the non-functional requirements, we use the heuristics. using the heuristics, we refine the modular architecture and we obtain what we call the physical architecture. So it's a refinement process implementing non-functional requirements using heuristics to obtain the physical architecture. The main artifacts related with the functional architecture are functional hierarchies, functional, and the n-squared chart for representing functional interfaces. So we represent the items that, for example, item 1 in this n-squared chart, the convention is input in columns. So item 1 is an input of F1. Item 2 is an output of F1 and an input of F2. And F5, item 7 is an output to the exterior of the group of F5. Also, we represent functional flows, and we represent each function by a textual description. It's important to understand that when we have the functional architecture, and we have the first version that we call the modular architecture, where we allocate the functions to different modules, we need to build what we call the refined architecture. To build the refined architecture, we use trade-off techniques and heuristics. Trade-off, currently we are using trade-off for identifying the best technology for each component of the architecture. So we use trade-off analysis to select the best technology based on some criteria, trade-off criteria. Unfortunately, I have no time. We have a paper recently published. If you are interested, please send me an email. I will send it to you. Here I will talk about heuristics, how we implement non-functional requirements using heuristics. Heuristics is the bridge between quality attribute models and the physical architecture. So heuristics describe how a quality attribute requirement, or also known as non-functional requirement, can be implemented through some design decisions to meet them. Heuristics use knowledge from various quality reason frameworks. So it's important. You have to build your quality model and the heuristics you need for your domain of application. And I recommend you, if you build that, don't publish it. It's an asset, very important asset for your organization. It's a very important asset, the quality model and the heuristics to implement the quality attributes. It's a very important asset in each company. So we have heuristics related with different quality attributes. For example, heuristics related with safety, heuristics related with performance. From the requirements tree, we apply the different heuristics. It's very important in some cases that there are conflicts between heuristics. For example, it's typical. Performance is in conflict with security. Performance is in conflict with safety, because safety measurements, safety implementations, some cases produce that the system is more slow. The same case with security implementations. When we apply the heuristics, we obtain what we call the refined architecture. So this is the quality model I defended in the book, in the ISE&PPOA, but you have to adapt this quality model to your organization or your projects. Here in our quality model, the main quality attributes are reliability and maintainability, efficiency, safety, and resilience. For these quality attributes, we collect from the literature and from experience heuristics. In the chapter 6 of the book is the collection of heuristics I collected during the last 20 years. We have heuristics related with systems architecting. Some of them are from the book of Rechting, the Rechting and Meyer book. It's a very good book, The Art of Systems Architecting. Some heuristics are from other sources, for example, reliability and maintainability, heuristics related with efficiency, heuristics related with safety, and currently heuristics related with resilience. very interesting right now. There are other heuristics applied to software architecting using the PPOA architectural framework. These are heuristics for the PPOA framework, that is a real-time systems architectural framework. When we apply all these things, allocation, trade-off, and heuristics, we obtain the final physical architecture that we call refined physical architecture. In this refined physical architecture, we represent hierarchies of parts, internal block diagrams for representing the interaction between the parts, and functional flows allocated to the parts. So F2 is a function allocated to part B, to this part. F2 is allocated to part B. In this functional flow, we have functions that are parallel or alternative. In this case, we can have functions that are sequential. In the Alfonso will illustrate it in the electric parking brake system. Here is an example how we apply heuristics. In this example that is in the book is a collaborative robot developed by Carlos, the co-author of the book, in the university in Holland. In this example, we have a collaborative robot that is an arm. In this arm, the robot has a skin of sensors to avoid harm to people that is near the robot. Okay, we here apply a safety principle, an heuristic that related with safety, that is the heuristic avoid non-deterministic behavior. So this heuristic is implemented considering this component, because we think that trajectories, there is a database of trajectories. We do not allow any trajectory. We have some predetermined trajectories. This is one way to avoid non-deterministic behavior. So the application of these heuristics is a new component, that is this trajectory database. There is another implication of this heuristic in the behavior. To apply this heuristic in the behavior and to avoid non-deterministic behavior, we control the behavior areas when we will allow some interruption. So we will allow undeterministic behavior. So we will allow undeterministic behavior in the last step of the manipulator. When the manipulator has, the gripper has picked the thing, and the gripper has the thing and is moving the arm to put it in the stack. In this moment, in this time, we have an interruptible region to allow these interruptions. Thus, it's the only place in all the flow, on the behavior flow, when we allow undeterministic behavior. This is a difficult issue to build. So it's an example of how we apply heuristics, in this case, at the software level. You can apply the heuristics at the system level or at the software level. This sample is at the software level. In INCOSE International Symposium 2021, I will explain the heuristics application to the system level, but more or less it's the same. Why is for us so important the functional architecture? We think it's very important because first, for us as engineers, the function is a transformation of inputs into outputs. And we apply a very important principle borrowed for buildings architecture This is a principle settled by an architect named Louis Sullivan in the 19th century, that is form follows function. So you design the building based on the functionality of the building. So for us, the functional architecture is the core, the artifact that is the core of the system architecture, because it's very important to allocate functionality and performance requirements to have a good functional architecture. It's very important to system safety analysis. It's very important to development of mechatronic systems, because the functional architecture is the core model that is built independent of the technical solution, and is the frame that integrates diverse engineering specialties. Alfonso will explain later the steps we follow to build the functional architecture. That is, identify the hierarchies, applied in a hierarchy to group the elements in a hierarchy, identify the functional flows represented by an N-squared chart, and from the N-squared chart and the hierarchies, obtain the functional flows. It's better to, when Alfonso explained the example, you will understand it better. The functional hierarchy is the must cover all the system functionality, and it is important to have high cohesion between the functions in the functional hierarchy and sequential cohesion. We mean by sequential cohesion, the output of a function is used as an input of another function. It's very important so to have consistency between the functional hierarchy and the functional flows. Functional hierarchy might be developed either top-down or bottom-up. As we will explain by Alfonso, we use for representing functional interfaces the functional N-squared chart. So we represent functions in the diagonal, and we represent the items in the column, input items in the columns. So this item is an input from to function B. With this information, we can represent seamlessly the functional flows, and it's very important. So from the N-squared chart is a very important input and very schematic way of representing functional interfaces, and very helpful to identify the main functional flows.